everyone, welcome back to Windows 8 Studies. I hope you all are doing well. So, we were discussing neurobiology, in which we have already covered the structural aspect of neurons, and we also discussed about neuroglial cells. We also discussed that how different types of glial cells they does the myelination on the axons of the central nervous system and peripheral nervous system. In the last lecture, we discussed about the different types of ion channels that are present on the membrane of the neuronal cell. From today onwards, we are going to learn about the electrical properties of neurons, which makes the neurons the excitable cells. Today's topic of focus will be resting membrane potential. So today we will be discussing resting membrane potential. So let's say that this is a plasma membrane of a cell. And this is the extracellular side. So this is extracellular matrix, and this is the cytosolic side. So this is the inside of the cell, and this is outside of the cell. So generally, there are some ions distributed equally. So some ions distributed randomly in the extracellular matrix and cytosol, but the charge distribution will be equal. Okay, so this is the general scenario. But when this cell is a neuronal cell, so let's assume that this is a neuron, the distribution of ions, the cations and anions, is unequal. So we have already discussed this in previous classes that the sodium ions will be higher on the extracellular side, as well as chloride ions will be higher on the extracellular side, while the cytosolic side will have anions and as well as the potassium ions. Okay, so there is the unequal distribution of those ions, which gives overall negative charge to the cytosolic side of the membrane in neurons, while it gives a positive charge to the extracellular side of the membrane. And this charge separation, which is due to unequal distribution of ions, this gives rise to electric potential or voltage across the membrane, which is recognized as the membrane potential. So the membrane potential is the electrical potential or voltage which is generated across the membrane due to the unequal distribution of the ions. So this is written as Vm. So Vm means the membrane potential. That is due to the unequal distribution of ions. So it is written as V inside. So this is the voltage which is on the inside inside the cell, the cytosolic face of the plasma membrane, minus the extracellular side of the plasma membrane. So this equation gives us the membrane potential of a cell. So the membrane potential of a cell when cell is at rest, when cell is at rest means it is not receiving any stimulus, this membrane potential is known as resting membrane potential. Okay, so whenever there is no stimulus across the neuron, that means cell is at the rest, that membrane potential is known as resting membrane potential, which is negative. Okay, which is negative. Why? We already saw that it is negative due to the due to high number of anions on the cytosolic side and high potassium ions on the cytosolic side. So the cytosolic side has the concentration of anions is higher there compared to the extracellular matrix, which gives overall negative charge. So that is why the resting membrane potential of neurons is negative. It is negative. Okay, I hope this is clear to you all. So conventionally, the direction of current is the direction of the flow of positive charge, right? That is why we can say that the anions, sorry, the cations, they move in the direction of current, while the anions, they move in opposite direction of what the direction of current is. Okay, so just remember this because by what conventionally the direction of current is direction of flow of positive charge. This will be helpful in upcoming lectures. Okay, so the this charge separation. Okay, so let's say that there are three positive ions outside and two negative anions. So while there are three positive ions inside and three negative ions. So this is giving overall negative charge to the cytosolic side of the membrane and a positive charge towards the outer side of the membrane. Let's say that we add some positive ions towards the extracellular side. Okay, so I'm increasing the positive charge on the extracellular side. So this is making the extracellular side more positive. Okay, let me draw this again. Okay, so this is the scenario 1 and this is scenario 2. So I'm adding more positive charge on the cellular side. So due to the increase so due to adding cations on extracellular side, this is increasing the charge separation. And this increase in charge separation is making the cytosolic side more positive, more negative, right? This state is known as hyperpolarization. This is what we call as the hyperpolarization of membrane. Whenever the charge separation is increased, making the cytosolic side more negative, this scenario is known as the hyperpolarization of membrane. But let's say instead of increasing the charge separation, we decrease the charge separation. So let's say instead of adding the cations on the extracellular side, I start adding cations on cytosolic side. Okay, so I start adding cations on the cytosolic side. So this will results in the decrease. This will result into the decreasing the charge separation because the cytosolic side was negative, and as I'm adding cations there, the overall negative charge will be decreased. So overall negative charge is decreased. So this is decreasing the charge separation. So whenever we decrease the charge separation, we say that the membrane is getting depolarized. This is what we call as the depolarization of membrane. Okay, let me sh let's understand this numerically. Let's say the membrane potential. So the membrane is negative on the cytosolic side, positive on the outer side. This is out, this is in. So let's say the membrane potential, this resting membrane potential in this case is minus 70 millivolt. So there could be two cases. Due to the addition of positive charge on the cytosolic side, I take this minus 70 millivolt to minus 50 millivolt. Okay, so I'm decreasing the charge separation. Initially, the charge separation was minus 70 millivolt, but now I have added more cations on the inside, and this is making the membrane, which the cytosolic side of the membrane less negative. So this is making cytosolic side less negative. Means I'm doing the depolarization of membrane. While if I add cations on the extracellular matrix, this will increase the overall positive charge outside the cell, and this will result in the making the membrane potential more negative. So the membrane potential will, let's say, it reaches up to minus 100 millivolts. So it will make the membrane potential more negative. This state is known as hyperpolarization. Okay, so to summarize, whenever you increase the whenever you increase the charge separation and you make the membrane more negative on the cytosolic side, that state is known as hyperpolarization state. So you are hyperpolarizing the membrane. While the depolarization is exact opposite. Whenever you decrease the charge separation, that state of the membrane is known as depolarization state of membrane. So keep those terms in mind when we will discuss about the nerve impulse conduction, how the membrane gets depolarized and hyperpolarized. Those terms will come in handy. Okay. So now we have seen what happens in the cell, in the neuronal cell when it is at rest. Let's take a look at the glial cell. So just like neuronal cell, glial cell also have sodium ions concentration higher on this extracellular side and chloride ion concentration higher on the extracellular side. While they have potassium ions on the inside of the cell and much more anions. Anions like the phosphate groups on the ATP, okay, which gives us its negative charge, then a lot of amino acid which has negatively charged residues on it. This overall, those negative charge is higher on the inside of the cell compared to the outside. So this scenario is same. Just like neuronal cell, glial cell also have the overall negative charge inside the cell. But glial cells, they are permeable to potassium ions only. Okay, so they do not lead the exchange of sodium ions, they do not lead the exchange of chloride ions, the calcium ions, or let's say any kind of anions. Okay, so the exchange of those ions is strictly prohibited. It is permeable to potassium only. So what happens is that the membrane has some potassium ion channels over it. Okay, so this is potassium ion channel. So this potassium ion channels, so what scenario is the potassium ions, they are fewer on the outside of the cell and much more higher in the inside of the cell. So this gives overall negative charge. Okay, so we already know this. So what happens is according to the electrical gradient. So the overall positive charge is here, right? So according to the electrical gradient, potassium ion should move from towards the negative charge. So potassium ion should move from outside to the inside. So if we take a look at the electrical gradient, the electrical aspect, or let's say instead of calling it as electrical gradient, let's call it electrical driving force. Okay, so electrical driving force is from outside to inside. Because potassium is a cation, so it is positively charged, and positively charged ions should move towards the negative charge. So they should move in the direction of the current, and this is the direction of the current from positive to negative. So this is the direction of current. So, so this should be the direction of the flow of the potassium ions according to the electrical driving force. So the flow should be outside to inside. So this should be the direction. But if you take a look at the concentration gradient, so if you take a look at the chemical driving force, it is clear that the concentration of potassium ions is higher on the cytosolic side compared to the outside. So the potassium ions should move from inside to outside. So they should move from in to out. So this should be the direction of the flow. Okay, so this is this is very controversial. This is very contrasting to each other. That the chemical driving force says that the potassium ion should move from inside to outside, while the electrical driving force says that potassium ion moves from outside to inside. So we are in the last lecture when we discussed about the leak ion channels. So the potassium leak ion channels. Okay, so they do not need any stimulus to open, so they open randomly. Okay, so as they open randomly, they are going to allow random exchange of potassium ions. Okay, so this random exchange of potassium ions due to there will be random exchange. So at some times the potassium will be moving out, and at the same time the potassium will be moving in. So let's say that this particular channel is moving the potassium from inside to outside, while this particular channel is moving that from outside to inside. And then at the next second, they can reverse the direction of the ion exchange, right? So the exchange of ion, the potassium exchange will go on and on till the equilibrium is reached. And when the equilibrium is reached, that equilibrium is known as potassium equilibrium, and it is written as EK. Okay, and this equilibrium constant, this is measured by using Nernst equation. Okay, I hope you have learned this in chemistry, that Nernst gave an equation to determine the equilibrium constant across the membrane, and this equation is RT by NF log of concentration of the ions outside the cell and concentration of ions inside the cell, where R is the gas constant, T is the temperature, room temperature, the F is the Faraday constant, and N is states the charge on the ion. Okay, so in this case we are discussing this for the potassium ions. So the equilibrium, so EK would be, so we are discussing this at room temperature. Okay, so room temperature, and the gas constant is already a constant, while N is equal to the 1. So by putting all of those values, it comes 25 millivolt. Okay, and when we change the ln value to log base 10 value, okay, by putting all of those information, it gives us the 58 millivolt value. Okay, 58 millivolt divided by N into log base 10. Oh, oh, just a second. Log base 10, the concentration of ions outside the cell divided by concentration of ions inside the cell. When you put the value, the concentration of potassium ions outside the cell and concentration of potassium inside the cell, the value of the value of the potential that it gives is minus 75 millivolt. So in the case of the glial cell, the resting membrane potential is minus 75 millivolt. So this is how we calculate the resting membrane potential. The equilibrium constant for the potassium, the equilibrium is reached due to the potassium leaky channel. So they randomly open that allow the exchange of the potassium ions. So potassium ion will be exchanged, but you can see the electrical driving force and chemical driving force, they are exactly opposite. So there will be no net flow of potassium ions, which will maintain the overall negative charge. Okay, so this is why, because the electrical driving force says otherwise. The electrical driving force says that the ion should move from outside to inside, while chemical driving force says that the potassium should move inside to outside. And this so this, this balances out, those two driving forces balances out. So there will be flow of potassium ion channels, but some potassium ions will move from in to out, some will move from out to in, but there will be no net flow, which will help us maintaining overall negative charge on the inside of the cell. Okay, so I hope it is clear why instead of why even though the cell has unequal distribution of ions, why doesn't normally ions get diffused and they distribute themselves equally? Because the electrical driving force and chemical driving force, they are balancing each other. So the overall negative charge, so overall charge separation will be same in the glial cells. But the case is otherwise in the neuronal cell. Let's say what happens in the neurons. So the glial cells, they were permeable to potassium ions. So the question was like, even though like in the normal cell, whenever there is unequal distribution of ions, then the channels will allow the diffusion according to concentration gradient, and that unequal distribution will be balanced and it will not, there will be no charge separation. But in the glial cell, the driving forces, the electrical driving forces and chemical driving forces, they balance each other, which which eventually results into no net flow of any kind of ions. Again, if you ask me about the sodium ion channels present here and there, the sodium ions cannot pass through this membrane, then anions cannot pass through this membrane, then the chloride ions, they cannot pass through the membrane. So there are anions here, chloride ions here, sodium ions here. Okay, the higher percentage of sodium and chloride outside and higher anions inside. So to all those ions, the membrane is impermeable. So but it can reduce the charge separation by the diffusion of potassium ions. But why doesn't it happen usually? Because the driving forces, they balance each other, resulting into the no net flow of potassium ion channels. But unlike the glial cells, neuronal cell, they are somewhat permeable to sodium ions, chloride ions, as well as they are selectively permeable. Like even though permeability is low, but they are permeable. Okay, and they are selectively permeable to potassium ions. Then why doesn't the charge separation gets reduced over the time in the neuronal cell? Let's learn about that. So this is a neuronal cell membrane, okay, and there will be sodium ions here. Okay, I'm not drawing this, I'm not writing sodium ions inside because the concentration is low. So by default, assume that. Okay, and then anions will be high here. So let's just, anions will be higher here, and there will be potassium ions. Okay, So there will be some sodium ion leak channels, potassium ion leak channels present on the membrane. So how does the resting membrane potential is maintained? So resting membrane potential is overall negative, right? So how does it maintained? You have the ion channels, you have the concentration gradient. So why doesn't the ion flow according down to the concentration gradient and make the charge separation zero? So what happens is that the leaky sodium ion channels should move the sodium ions from outside to the inside. Why? Because the outside, the charge, the concentration of the sodium ions is higher on the outside, right? So the movement according to the concentration gradient should be from outside to inside. Okay. And according to the chemical, so this is according to the chemical, so the chemical driving force. So this is chemical driving force. And according to the electrical gradient, you can see that the inner side is negative and sodium ion is a cation. Okay, it is a positively charged ion. So it is a cation should move from positively charged area to negatively charged area. So again, the chemical driving force is also from outside to inside. So now, unlike in the glial cell, the both of the driving forces were opposite, and that is why there was overall zero flow of the. And so there was no net flow of the potassium ion. But here you can clearly see that the both electrical and chemical driving forces means the electrochemical gradient is down, like it is out from outside. Electrochemical gradient says that the movement of sodium should be from outside to inside. But then why doesn't it happens? Because the ion flux, this doesn't depend on the electrochemical gradient itself. It depends on the electrochemical gradient as well as the membrane conductance. So it depends on the electrochemical gradient, which is written as the electrical driving force plus chemical driving force. Okay, so this is the electrochemical gradient into membrane conductance. Okay, so the ion flux, that whether the ion will move from outside to inside or inside to outside. So flux means the movement, overall movement. Okay, so the ion flux will depend on the electrochemical gradient as well as the membrane conductance. Okay, whether the membrane has high conductance to that certain ion or low conductance to that certain ion. So what happens is that even though sodium ion channels, sodium leaky channels are there on the neuronal membrane, but the concentration of the sodium ion channels is very low compared to the leaky channels of the potassium ions. Okay, potassium leak channels. Okay, so the sodium ion channels, sodium leak ion channels, they are very few in number. So this gives the low membrane conductance. So the due to the presence of fewer sodium ion channels, the conductance, membrane conductance is very low for membrane conductance is very low for sodium ions. So even though the electrochemical gradient is high, but due to the low membrane conductance, overall ion flux of sodium ions will be low compared to the potassium ions. Okay, so what happens is that the electrochemical gradient, it is higher for, okay, we are discussing this for sodium ions, but the membrane conductance is low, and that is why the overall ion flux, sodium ion flux, that will be low compared to the overall potassium ion flux. Okay, so I hope this is clear to you all, like why in the neuronal cell, even though they has those potassium, sodium leaky ion channels, they do not show the influx of sodium ions. So there will be influx of sodium ions, but that will be quite low compared to the potassium ion flux. Okay, so there will be the sodium influx, but that will be very, very low. Okay, so this is how the resting membrane potential is maintained. But there is one, so this is the passive. This is the passive scenario. So here there's no involvement of ATP in the either in glial cells or in the neuronal cells. No ATP is required for those for this maintenance. But there due to, so the resting membrane potential is also maintained due to pump known as sodium potassium pump, and in this case the ATP is involved. So this is a pump. Okay, ion channels are different from pumps. Ion channels do the passive diffusion, so that they do the passive exchange of ions. Okay, so channels, they exchange the ions passively. Okay, so there is no involvement of ATP, and they do that according to the electrochemical gradient. So the movement of ions is down the electrochemical gradient. While in the pumps, the ATP is used. So this is active transport. And that is why, as it is, why do we need ATP? Because we are exchanging the ions against electrochemical gradient. Okay, so the against the electrochemical gradient, the pump does the exchange of sodium and potassium to maintain the resting membrane potential. So what happens is that on the membrane, this is the sodium potassium pump. This this does the efflux of sodium ions. So three sodium ions are pumped out and two potassium ions are taken in. So this does the efflux of sodium ions. Efflux means the movement is from cytosolic side to the extracellular side, and the two potassium ions influx is done by the ATPase pump. So this is sodium potassium ATPase pump. This requires ATP. Okay, this is sodium potassium pump. Okay, so this is the movement of ions in this pump. So what happens? The sodium ion concentration is already high on the extracellular side, but due to this pump, the concentration is maintained. So the sodium ions is increasing continuously on the outside, while the potassium ion is increasing continuously on the inside due to this pump. So this is against the electrochemical gradient, and this is how this pump maintains the resting membrane potential. So I hope what is resting membrane potential and how by the different mechanisms it is maintained, that is clear to you all. Should we summarize it? Okay, let's summarize it. So resting membrane potential, okay, the lecture was quite long. Resting membrane potential is the membrane potential of the neuronal cell when the cell is at rest, means there is no stimulus. So that this is overall negative. So this ranges from 60 millivolt to 70 millivolt to negative minus 70 millivolt. Okay, this is the overall negative. The range is from minus 60 millivolt to minus 70 millivolt. So this resting membrane potential, it is maintained. This is generated or it is maintained first due to unequal distribution of ions. Okay, do not forget this unequal distribution. The in sodium ions and chloride ions will be high on the outside, while the potassium ions and anions will be high on the inside of the cell. Okay, then due to the impermeability of neuronal membrane to anions, This is also maintained. So even though the cations can move from inside to outside or vice versa, the anions cannot move from inside to outside, and this helps us maintaining the overall negative charge on the inside of the membrane. Then the resting membrane potential is also maintained with the help of sodium potassium pump, which actively transports the sodium ions and potassium ions against the electrochemical gradient. So this is how the resting membrane potential is maintained in the neurons. In the glial cell, how does it maintain? Because the overall the driving force, the electrical driving force and chemical driving force, they does the exchange of the potassium ions, but the overall flow of the potassium ions is zero, and that is why the charge separation is maintained. But in the neuronal cell, even though there is electrochemical gradient for sodium ions, the sodium ions are not, they are not they are not exchanged due to the low membrane conductance. So with this we are done with the resting membrane potential part. In the next lecture we will learn about the action potential, and in upcoming lectures we will see how the nerve impulse is conducted, the other properties such as depolarization and hyperpolarization and repolarization of membranes. Till then, see you. Bye bye.